Hello, hope you're doing well. In this presentation, I would like to talk about Benders decomposition as a reformulation technique for solving NP-hard optimization problem. In this presentation, I first talk about the concept of Benders decomposition, its definition, and how it works. And then I provide an example using generalized quadratic assignment problem as an NP-hard optimization problem, as it is a non-linear optimization problem, and it's very complex. And then I use the formulation linearization technique to define different linearization of the JQAP. And after that, we analyze all the formulations of the JQAP using RLT technique. And then, based on these linear reformulations, we develop a Benders decomposition for the proposed problem and provide some computational results and the conclusion and the references. Benders decomposition is a well-known optimization technique that is suits for mixed integer linear programming models. When you have both binary and non-binary optimization variables and constraints. So it suits for NP-hard optimization problem that we can decompose the structure of the variables. For example, such as the network design problems, when we want to first activate the arcs and then define the flow of the products or variables on each arc. Therefore, the Benders decomposition is very suitable for solving mixed integer programming models in different supply chains, logistics, and network design applications. So in the first step, we must be able to separate the variables and the constraints based on the binary and non-binary variables. Non-binary variables and constraints can help us to define a linear optimization problem, a linear optimization problem as a subproblem. The main advantage of linear optimization problem that is very easy to solve, and we can define the dual of a subproblem very easily. And in another way, for binary variables and constraints, we create a master problem that have some difficult constraints. And based on the dual of subproblem, we can create feasibility and optimality costs which can be added to the master problem. So it creates a cycle that at each iteration, we need to update the feasibility and optimality costs and run the master problem to see that how we can improve the solution to find a near optimal solution. And the main advantage of Benders decomposition is has a very time efficiency for solving larger scale and complex problems. So the problem under study is generalized quadratic assignment problem. In this problem, we have a set of centers, facility centers or production centers, and a set of equipments. And we want to assign the equipment to these centers. And we have two costs. The first cost is the linear assignment cost. And the second one is a quadratic interaction cost, which includes the distance between the facilities and the flow of the products between the assignments. So, and each equipment has a space or can be considered as a demand, and each facility, each center has a capacity, and we need to assign equipment to the centers where we have an objective function includes two terms. The first one is the linear assignment cost. A second one is a quadratic cost that shows the assignment of the interaction costs between the facilities and equipments. So as a assignment we have in constraint number 2, we need to ensure that each equipment must be assigned to one facility, and we have a capacity constraint for the facilities that the capacity of the centers is limited, and the main variable is a binary variable. So it is known as a well-known NPR optimization problem, which is a combinatorial optimization problem. And this problem is non-linear due to the second term in the objective function. It is also an NP-hard optimization problem due to complex constraint, assignment constraint in as a number 2, and the capacity constraint number 3, which makes this problem as NP-hard. But we cannot apply a Benders decomposition to this model. Why? Because as you can see, it only includes the binary variables. So we first need to define a linearization for this problem. So the objective function is nonlinear. So we can replace the xij multiplied to xkl using a new variable which is non-binary. So we can replace the in the second term objective the variables xij xkl with yijkl, where we need to have additional linear constraints to provide a link between this new continuous variable, or this non-binary variable y, and the variables x, xij and xkl. I think everyone knows about this concept because such linearization are very well known for the course of operation research. But in our point of view, we know that xij multiplied to xkl is the same as xkl multiplied xij. Therefore, we can replace variable y kl ij with the variable y ij kl. Therefore, for the new variable y ij kl, we have the same condition as the variable y kl ij. Therefore, this links variable can be reproduced for the variables y kl ij, as you can see in the constraints 8, 9, 10. Therefore, we added new constraints to the model, constraints 5, 6, 7 as for the original model, or we can use the constraints 8, 9, 10 for the second model. Now we want to apply the RLT. RLT help us to define different reformulations for the constraints to make the constraints with linear variables. So we first focus on the capacity. First focus on the assignment constraint. The constraint number 2 was the assignment constraint. We can multiply both sides of this equation for the constraint number 2 to a non-negative variable x K-L. Therefore, we can define a new variable and a new constraint named as constraint number 11. In addition, for the capacity constraint, which has also includes binary variables, we can multiply to both sides of this constraint to the term of 1 minus x K-L, because the term 1 minus x K-L is also a non-negative variable. Therefore, there is no change in the constraint, and it would be written as equation number 12. After that, we have new equations that we instead of multiplication of two integer variables, we use variable y to define a new constraint. Therefore, we add the constraint 13 and 14, and we can add constraint 15 and 16. That, as can be seen, these constraints, the constraints 13 and 14 are the reformulation for the assignment constraints, and constraint 15 and 16 are the new reformulations for the capacity constraint. So, using this new reformulation, we can define a linear model for the JQAP. So, the first model can consider all equations. However, this model has many equations and many constraints, and we know that more constraints makes the problem difficult and increase the CPU time. Therefore, we can define different reformulations based on these new constraint. One idea is only to have the term for the to keep only the constraints 13, 14, and define it as a model R2. So in addition to model R1 and model R2, we can define other reformulations. So each reformulation, as you can see, uses a set of constraints. And we can see that based on these constraints, how it affects on the optimality and the quality of the solutions. Some results based on some benchmark for GQAP are provided here, and based on these results, we can see that the first issue is that the linear models can provide a fast solution compared to the original GQAP, because they are linear. However, GQAP is non-linear, and some of them has provide a better estimation for the optimization problem. I should say that for all these reformulations have been solved by Ciplet solver, and we can see that the reformulation R2 is more suitable if we consider both criteria of optimality, the optimal gap, and the CPU time. Therefore, based on these reformulation, we choose R2 as the base, as the best one. Now we want to apply the Benders decomposition. As we discussed earlier, the reformulation R2 model is a linear model, and it is a mixed integer linear programming because it has both binary and non-binary variables. Therefore, we separate the R2 model into two dependent problems, the master problem and the subproblem. So for the primary subproblem, we can consider only the second term of the objective function, which is the quadratic term. And also we can consider only the linear constraints that that are existed from constraints 13 and 14. Therefore, we assume that based on the fixed version of the Xij, we can solve this linear model very easily because it only has some linear constraint, and the objective function is also linear. Therefore, as it's linear, we can define the dual of this model. As you know, the optimal value for the dual of subproblem or the primary subproblem has the same value. Therefore, the dual of the linear model is the same as the linear model. So we define it, the dual subproblem, as follows. And based on this dual of the primary subproblem, we can define an optimality and feasibility cut, where we can consider the term of 25 as a optimality cut. Therefore, the Benders decomposition reformulation model in the master problem has the first item plus the cost P, where the cost P should be updated using the equation number 25. So in the Benders decomposition, at each step, we need to first define a random feasible solution for Xij, and then run the dual of subproblem to estimate the variable P, and then we run the final master problem. So using these equations, we can see that the Benders decomposition model has a very the same constraints similar to the main model, because it only has one additional constraint, number 25, compared to the original model, which was non-linear. However, this model is linear, and we can solve this model much easier when for solving large scale optimization problems. So the Pesito code for the how it algorithm works can be defined as here. So there are two termination criteria. The first one is that we reach the maximum number of iterations, and the second one is that the solution from this dual of subproblem and the master problem would be the same. And using this equation, we update at each time the solution from the dual of subproblem and finally the master problem to achieve an optimal solution. Yeah, in our computational results, we compare the optimality gap and the CPU time for the Benders decomposition and some other reformulations model, and we can see that the Benders decomposition is faster than majority of the reformulation techniques, and it also has provide a better optimality gap in majority of cases. So this presentation, I tried to focus on the definition of the Benders decomposition for the simple quadratic assignment problem. And we first define a linearization for the GQAP and then provide different reformulation for the constraints to define a new mixed integer optimization problem for the GQAP, and then apply the BD formulation. We can see that the BD formulation can solve the all the instances much easier, and that we can use the BD decomposition BD model for validating larger scale instances. When we apply Meteor's algorithm in larger scale, we don't know about an optimal solution and how our solutions are close or far from optimality. Therefore, a Benders decomposition can help us to have an estimation of the optimal solution, and then we compare the solutions of our heuristics in larger scale instances with the BD reformulation. For more information about this paper, I highly recommend you to search this paper and read it. In this paper, I not only use the Benders decomposition, but I apply different heuristics and an efficient adaptive large neighbor search algorithm for solving the generalized quadratic assignment problem. Please read it, and if you have any questions, please let me know. I would be happy to answer your questions and comments. I also should say that all the data for this paper are available in the supplementary materials of the paper, and you can search it and download the data, and you can provide and define your algorithms for this data. Thank you for your time and have a good day.